In the previous video, we studied the Oswald dilution law. In this video, we are going to study the autoionization of water and pH in detail. Now we are going to study the autoionization of water. We know that pure water does not dissociate completely. It does dissociate to a smaller extent. So now let us see how the equilibrium reaction for the autoionization of water looks like. So here we are going to take two molecules of water. You can see it is splitting up as H3O plus OH minus. So what happens here is 1H from one water molecule is donated to the H2O group, which forms the hydronium ion. So H3O plus is called as the hydronium ion and OH is called as the hydroxyl ion. Now we have to write the equilibrium constant. We know that the equilibrium constant is denoted by the letter capital K. So the equilibrium constant for the autoionization of water is given as K is equal to whatever entities are there on the reactant on the product side, you are going to mention up in the numerator, and the one which is on the left hand side will go in the denominator. Hence you will get K is equal to the molar concentration of H3O plus product or multiplication sign molar concentration of OH minus ions upon 2 times H2O. Okay, so the molar concentration of H2O molecules which are 2 times. Now here you saw that the water did not undergo complete dissociation, hence you can take the concentration or the molar concentration of water as constant. Now since we have taken K as the equilibrium constant, now we are taking the constant value for water as K dash. Now the term which is in the denominator, that is 2 times H2O molecule, you shift it along with K. Okay, now we know that the molar concentration of water is considered as K dash. So this equation will become as K into K dash is equal to H3O product OH minus ions. And this K into K dash is nothing but Kw, and Kw here is called as the ionic product of water. And how do you define this ionic product of water, which is represented by Kw? It is the product of the molar concentrations of hydronium ion and the molar concentration of hydroxyl ions at equilibrium in pure water at given temperature. Okay, now here it is found out that the molar concentration of hydronium ion is equal to that of the molar concentration of hydroxyl ions. So the value which was estimated was about 1.0 into 10 raised to minus 7. So what you will do here, Kw is equal to, just substitute the value, that is 1 into 10 raised to minus 7 into 1.0 into 10 raised to minus 7. On multiplication you will get 1.0 into 10 raised to minus 14. So this is the ionic product of water. Now we are going to study about the pH scale. The definition of pH and pOH was given by Sorensen in the year 1909. The definition of pH is negative logarithm to the base 10 of the concentration of H plus ions in solution in mole dm cube inverse. So the equation for pH is written as pH is equal to minus log to the base 10 H molar concentration of H plus ions. Now let us study the definition of pOH. pOH is defined as the negative logarithm to the base 10 of the molar concentration of OH minus ions in the solution. So now let us look how the equation looks like. It is written as POH is equal to negative log to the base 10 molar concentration of OH minus ions. I told you the two brackets there, they represent the molar concentrations. So whatever is given in the terms of definition for pH and POH, you just have to frame it in the equation form for the same. Now let us study the relationship between pH and POH. We know that ionic product of water is written as Kw is equal to molar concentration of H3O plus, that is hydronium ion, product to the molar concentration of OH minus ions, that is hydroxyl ions. We also derived the value of Kw, that was 1.0 into 10 raised to minus 14 at a given temperature, so that was at 298 Kelvin. Now just substitute these values in the above equation. Now we have to take logarithms or log on both the sides. So you know, according to log AB is written as log A plus log B. So here we will write it as log to the base 10 H3O plus ions plus log to the base 10 OH minus ions, which is going to equal to minus 14. So 1.0 into 10 raised to minus 14 according to log is going to give you the value minus 14. If I want to cancel minus sign of that number 14, then I have to multiply the entire equation with the negative sign. So what would I get then? Minus log to the base 10 H3O plus ions plus minus log to the base 10 OH minus ions is equal to 14. Now that minus and minus sign will cancel each other, just giving you positive 14. Hydronium ion is very much acidic in nature. So now this H3O plus here is nothing but H plus. Okay, so you can write it as minus log to the base 10 H plus in place of log to the base 10 hydronium ion. Okay, so what will the equation take the form as now? Minus log to the base 10 H plus minus log to the base 10 OH minus ions, giving you equal to 14, right? Now we know that minus log to the base 10 is equal to pH and minus log to the base 10 OH is equal to POH. Now the equation will take the form of pH plus POH is equal to 14. So you have to keep this equation in mind because it is very important for calculating the numericals. Okay, so this is the relationship between pH and POH. If you look at the pH scale, you know that it ranges from 0 to 14. 7 is considered as neutral, below 7 it is acidic, and above 7 it is basic in nature. Let us now study the acidic, basic and neutral solutions in detail. First we shall start with the neutral solution. Now we are going to consider the temperature range at 298 Kelvin. So whether you are taking pure water or any aqueous solution, we know that the molar concentration of hydronium ion is equal to the molar concentration of hydroxyl ions, which is having the value 1.0 into 10 raised to minus 7. If we are taking pH, we know pH is equal to minus log molar concentration of H plus ions. Now just substitute the values in here, so you will get it as minus log to the base 10 in the bracket 1.0 into 10 raised to minus 7. According to the basics of law, you are going to get it as 7. Hence the value of neutral solution is found out to be 7. Now we move on to the acidic solution. In acidic solution, the concentration of H3O plus ions, that is hydronium ions, is very much high when you consider it with OH minus ions, or you can simply say that the molar concentration of H3O plus ions is greater 1.0 into 10 raised to minus 7, which is the value of OH minus ions. So from this you can easily deduce that the pH of acid solution is going to be less than 7. Next is the basic solution. In basic solution, the concentration of OH ions are more when you compare it with the concentration of hydronium ions. So you can say the molar concentration of OH minus ions is greater than the molar concentration of hydronium ions. Or in other words, you can say that the concentration of hydronium ions is less than 1.0 into 10 raised to minus 7, which is the value of molar concentration of OH minus ions. Hence, the pH of a basic solution is greater than 7. So keep in mind, for neutral solution, pH is 7 and the condition is molar concentration of hydronium ion is equal to the molar concentration of hydroxyl ions. Whereas for acidic, what happens? The molar concentration of hydronium ion, which is also the H plus ions, is going to be more when compared with the molar concentration of OH minus ions. And when you look for the basic solution, the molar concentration of OH minus ions is going to be more when you compare it with the molar concentration of hydronium ions. So by now you know that hydronium ion is acidic in nature and that is only your H plus ions. So whenever you say acid, acid means a proton, that is H plus, and when you say base, it should be OH.